So welcome back. So we're gonna do module 7 now. So if you look at the course outline, we're pretty much done with 1 through 4. And then now we went through the transition where I said that, we'll be talking about the individual, 3, I would say, domain independent areas that we can cover in this class. I mean, there's a couple others that we cover in a longer semester, but then these are the 3 things that we'll cover. One is system optimization, and then you have uncertainty modeling, design and uncertainty type things, and then reliability engineering, and then we have single and multi-attribute decision analysis, right? So we'll talk about single and multi-attribute decision. Let's get started. So in the last few lectures, we talked about how system models can be very useful, right? So they actually set the stage for us to be able to do something. Okay, we also mentioned how decision analysis is an essential tool for concept selection, right? So the general idea is that we make ad hoc decisions in our life mostly, just in common sense or simplistic analysis, just probability, or this is more likely, that seems more lucrative. When we talk about more involved decisions, we start talking about multiple attributes or extreme outcomes, then we have to use formal methods. Otherwise, some engineering projects are billions of dollars, right? You don't just make decisions without careful thought and consideration and use all the tools that are available to you to make the best decision possible. Okay, so has anybody here had decision analysis in the past? You've had multi-criteria decision analysis. Okay, so and you're the only one, looks like. Okay, good. Okay, awesome. So we have one audience member that has done multi-criteria decision analysis. Today we'll cover from the basics of decision analysis and why it's important in system design. So systems don't get built in a vacuum, right? We talked about how decision makers are involved all the way from people who conceptualize the idea to people that use those systems, right? So, and humans make decisions, and you're always making this decision of whether to use this system versus that system, whether to fly fast or slow, whether to invest in a new technology or not, whether you use this dimension versus that dimension, this material versus that material, right? So all those decisions, if we can make in the best way possible, then we expect our systems to also perform in the best way possible, right? So, I broke this down into 2 parts, part 1 and 2, my presentation on decision analysis. So in part 1, these are the things we'll be covering. And then in part 2, we'll cover the remaining ideas, including some topics in multi-attribute decision making. Now, of course, as with most of the things, this is going to be much shorter than it is typically in a semester, but we'll try to do our best, and I'll try to cover all the main points that I want to get across here. So my assessment was that part 1 would be about 2 hours, and then part 2 would be about 1 hour. Okay, let's see how it works. So this is the agenda here. What is a decision? Some engineering examples, followed by some thoughts on uncertainty and what a good decision under uncertainty means, decision trees, and then decision-making axioms. Okay, so we all know what decisions are, right? What is a decision? So we got choosing a course of action. What else?
From a set of multiple actions.
So that's one of the definitions I get usually, right? So a decision may be looked at as choosing one among many alternatives, right? That's the source that I'm getting. That's the type of answer I'm getting. One of the things is that if I make a decision and I quickly say I'm gonna fly to Europe tomorrow, and I say, nah, it's gonna cost too much money. I'll rather just stay home, or I'll do something else. I'd rather go on a drive, right? So am I making decisions if I'm choosing an alternative or no?
Yes.
I'm making a decision, but I'm also constantly changing the alternative that I chose, right? So one thing that we'd like to distinguish from our definition of decision to what the commonly accepted definition is And that is actually correct, choosing one among many alternatives, but something has to be committed, right? So when we choose this decision, let's say of the 4 that I showed you, people say it's an irrevocable allocation of resources. As soon as you allocate resources, if I bought a ticket, then you can say I've made a decision. You can't say if I'm just thinking about it, right? So it's an irrevocable allocation of resources, and you can say it's an irrevocable allocation of resources to one alternative from a set of alternatives. That's fine. I mean, we're not against choosing one from many alternatives. We just want you to commit some resources to it. Okay? Right. So we say it's irrevocable because going back to status quo should cost money, time, or something along those lines. Okay? Something was committed. Going back would not be the same as status quo. Then you say you've made a decision. And it's an allocation of resources because those could have been used somewhere else. Okay? If I didn't spend time buying a ticket, I would have spent time. Even if I get a full refund to a ticket, I still wasted time, right? So full allocation. So it's an irrevocable allocation of resources. And once you think along these lines, then you start thinking, okay, well, that's why we talk about systems engineering projects or large-scale projects, because you have to think of every decision as an allocation of resources. In fact, just verbal agreement between people sometimes can be enough to get you in trouble. So, all right. So, why does such a field exist? Why do we have engineering decision analysis? Many times people say, oh, that should be in psychology or business at best. Why do engineers have engineers started talking about decision making? Because it's pervasive, right? Every day is a decision. Can we do a Tuesday class? Can we do, you can spend this time doing something else. All of you are deciding to be here. You're also deciding some career path for yourself. You're making decisions all the time. But even if you're working in an engineering firm, you think you're doing an engineering problem, but you're making decisions. I'm going to choose to use this material. I'm going to choose to pursue this design. Right? So you're constantly making decisions. And everyday decisions, we don't always say that, you should use a whole bunch of analysis for. I mean, you can make those decisions using your instincts, right? So if I decide whether to, go get food at this restaurant versus some other restaurant, those things are trivial. I can just make instinct. I feel like going here. And it's not even critical or prudent to sit down and analyze every basic decision in life. But formal methods, technical methods become necessary when you have extreme outcomes, right? If this happens, then major catastrophe happens and people can get hurt. If that happens, you lose millions of dollars. If you have major outcomes, then you have to analyze those decisions. You can't just do it by guesswork. Uncertainty, when the outcomes are not guaranteed, right? So if the outcomes were guaranteed, then you could say, if I do this, that happens. If I do this, that other thing happens. Well, let's do the thing that leads to the outcome that I want. That's not how life works, right? If you remember the graph that I showed you in the last lecture, is that, you chose this decision, this failure mode could happen, that failure mode could happen, 2 failure modes simultaneously could happen with different probabilities. So uncertainty makes decisions hard. All engineering decisions involve uncertainty and many attributes, right? You don't just buy things based on one thing, you buy things based on multiple attributes. You make decisions based on multiple attributes. If reliability was the only concern, everything would be over-designed and very expensive. If cost was the only concern, everything would be cheap. If people want trade-off, they say, okay, well, I want this performance level at this price, and this is my trade-off over those. Okay? So engineering decisions often involve extreme outcomes, uncertainty, and many attributes. That's why engineering decision-making exists. Okay? And many times we need to automate decisions, right? So when you're running an optimization algorithm, it's actually going through many, many decisions for you because you've said, I prefer this attribute to be maximized. Okay, great. It's going to cycle through all the solutions and find one that actually moves in that direction. So, and then people make bad decisions all the time. That's another thing, right? So, if everybody wasn't already making good decisions, again, we wouldn't have a field. People make bad decisions all the time. Bad investment decisions, bad medical decisions, and then bad engineering decisions. Right? Every company, I mean, if you look at companies that had monopoly almost in cell phone markets are no longer to be found, or they're no longer the leaders, made bad engineering decisions, right? And decision analysis has been successfully used in many, many fields. So oil and gas exploration is used, automobile industries use decision analysis, medical industries use medical decision making. So the field has existed for some time. It's grounded in mathematics, is pretty solid, and it's something that everybody should know. And the best thing about all these things that we talk about, domain independent skills, is that they change your way of thinking. If you have studied optimization, you start thinking of the world as objectives and constraints. If you have studied decision analysis, you start thinking of your life, many things that you do in life as a decision to be made under uncertainty. And that is a good thing, because now you know how we say we have now assimilated the knowledge, and now we're actually using it in our everyday behavior. So great. And then before we go, there is a distinction we like to make in decision analysis. We use terms like normative, prescriptive, and descriptive. Okay? So normative means that it's something a decision maker should do given their preferences. Means that if you give me your preferences over something, then I can prescribe, using decision analysis, the correct course of action. And that's what you should do. If you don't do then you're irrational. So it's a normative field. Prescriptive is pretty much the same as normative. It says that, it's prescriptive. This is what the decision maker should do given their preferences. Only normative things should be prescribed. And then finally, descriptive is something that describes an existing system, right? So how people make decisions. Psychologists will often concern themselves with, people under these conditions act irrationally. Well, we're not in the business of acting irrationally. Those are descriptive methods. In their own right, they are great. They help us understand the human mind. We are only interested in prescriptive and normative methods. And so descriptive is what a decision maker would do when confronted with a situation. And we don't teach that in decision analysis. Decision analysis is normative. It's a prescriptive way of making decisions, right? Because it's founded in mathematics. So that's that. Okay. So yes.
So I find the first two to be very similar.
They are similar. They are the same.
So what is the fine line of distinction?
Other than not really anything, it's just that I said these are the terms you will hear. So you will know that if you hear normative, they're pretty much saying the prescriptive, and prescriptive is normative, so on and so forth, right? So these are just definitions of terms that you would hear. So three elements of a decision: outcomes, uncertainty, and preferences. So what are the things that can happen? What is the associated uncertainty or likelihood of those events? And what are the decision maker's preferences? Okay. So it's simple, but it's very important that we distinguish between these three. People will often confuse between outcomes and uncertainty and preferences. It's very surprising to me that happens. For example, people say, outcomes are so lucrative, so uncertainty is irrelevant, right? People buy lottery tickets, or they will take undue risks because they're so enamored by the possibility of doing something. Like if you look at somebody wanting to be a movie star or a national sports hero, right? I mean, look at the likelihood of that happening. which is not to say that nobody should do this. I mean, if you think if there's capability, I guess you could pursue those areas. But they're so enamored by the outcome that they don't understand the uncertainty associated with it. Or in engineering problems, sometimes if probability of failures are too low, then people ignore them. So that's another human bias that we have, that when its probability is high, we think it's almost always going to happen. When the probability is low, we think it's never going to happen, as opposed to really grading probability with what the number is. So many medical procedures, right? So there's only 2.5% chance of failure. Well, 2.5% chance of failure for a medical procedure is a huge number. Okay, and similar. So outcomes are lucrative, so uncertainty not important. The probabilities are too low, so it doesn't matter what the course of action is. When people drive, let's say, under the influence of alcohol, or they drive carelessly, they think, oh, well, accidents rarely happen, so it doesn't matter, right? Not realizing when it does happen, the outcome is so bad. So in a simplistic sense, I'm making the same comment as FMEA, that, yeah, both severity and the outcome and the probability of that event happening are important. Okay, so some engineering examples. So GM, General Motors, decided to relaunch the Corvette in 1988, I think. And it was the first new Corvette in 13 years. It was actually, the decision was made using decision analysis. And it was actually it says engineering. It says it should be engineered. So it was considered by SAE the best engineered car of the 20th century. So it was a successful decision. It was done using decision analysis, where they considered all the uncertainty and the benefit of relaunching Corvette. Corvette had existed before. Okay, and then nuclear plant siting. That's another area where it's used quite a bit, or has been used in the past. Why is this a big problem? Where should we put a nuclear power plant? Why is this a... Okay, nuclear waste is one. What else? Okay, so you're saying it's an easy decision, right? Make it far away from people. What else will happen? What else? So it's not an easy decision now, you're saying. Okay, so it's a difficult decision because there's many competing factors. You don't want to be too close to a city. You don't want to be too far from a city. Because you need to have people working there, right? There won't be any stores nearby. And of course, transportation of workers, nuclear fuel for it to get there, and then spent fuel too. And sometimes they try to, hold the fuel after it's spent for some years before they dispose it. But either way, you see there's logistical challenges both ways. So it's not an easy decision, and it's not a single attribute decision either. It's not just one thing of generating electricity. It's also safety. It's also convenience. It's also all these other things. So, and if you think back to what I was saying, both these decisions involve extreme outcomes. If there's uncertainty and multiple attributes. So that's what makes decisions hard, and that's why they're using decision analysis for these problems. Okay, so next is uncertainty. Let me just make sure that I have my stopwatch going so that I don't make the same mistake I made earlier. Okay. So uncertainty is everywhere. Decisions almost always involve uncertainty, which affect outcomes. What is uncertainty?
So something that is not fixed, right?
Our confidence on the outcome? Right, so Right. So it is, we don't know, we don't have the complete knowledge of possible outcomes. We don't know what things can happen. We don't know how likely they are to happen. Right. And then it's also exists when we don't know what we want. Right. So there's a few ways we can think about uncertainty. But the accepted definition is uncertainty is lack of knowledge. Okay. Lack of knowledge. If we knew everything, past, present, future, we wouldn't have uncertainty, but we don't. And a term that we use sometimes is deterministic outcome, which is like things are certain when decisions lead to fixed outcomes. Very rare. Like, I drop something and it hits the ground. You could say that's certain, even though you could probably think of a very small probability that it won't happen, but let's say it's deterministic. But then the other term we use is stochastic or probabilistic, when a decision can lead to multitude of options, right? So the decision to buy a certain car, expecting a given performance or reliability, redesigning a component, planting crops, all those involve uncertainty. Like, I can take an action, I can take the same action twice and I can get different results, okay? Different realizations. How to incorporate uncertainty in decisions? We need a mathematical model of uncertainty. So we don't like to talk about, hey, I don't know what can happen, weather is uncertain, those kinds of things. That is not something that will work in systems engineering. It might rain tomorrow. That doesn't help me at all. Okay? The amount of rain tomorrow between 3 and 4 p.m. is normally distributed with mean 1 inch and standard deviation of 0.2 inches. Now, this is useful. This I can use to build models. If I'm collecting rainwater, I can predict how much water I'm going to collect. If I want to know whether the roads will be impassable, I can get some idea. Oh, hang on a second. Roads might be flooded because there may be too much rain or not enough rain, right? Those kinds of things can be done. But we're looking for mathematical models. When we say mathematical models of uncertainty, we're looking for probability distributions of random variables that are involved, right? So, in engineering, uncertainty means lack of knowledge about the value of a mathematical variable. So, diameter of a manufactured shaft, I have uncertainty. Its mean is this, standard deviation is that, or it is some other distribution, beta distribution, or some other exotic distribution. Gust loads on an offshore platform. When you have offshore platforms that are subjected to wind and gust loads together, you need to be able to design them to avoid failure by considering both of them simultaneously. Probability of failure of a rocket motor, probability of failure of a nuclear power plant, probability of the Earth being hit by a large meteorite. Okay? So these uncertainties must be characterized before one can make good decisions under uncertainty. Now, the last one, I don't know if you saw, I've been following this article about this asteroid that they said had less than 3%. Yeah, so they keep changing that, right? So we can evaluate those things based on our uncertainty model and then trajectory that we say, okay, well, this is the area that is going to be, and in these % of chances it intersects with the Earth, so this is the probability of actual impact with the Earth. So all of these are things that we can work with. So we characterize uncertainty using probability density functions, cumulative distribution functions, moments, and so on, right? So we need math models. You've had statistics, all of you, I'm assuming. So you could build those models, or at least apply those models. Okay. So related to uncertainty is this concept of probability. What is probability?
Chances of occurrence.
Okay. How do you find chances of occurrence of an event? How do you find the chance of occurrence of an event?
How do we find it?
Mm-hmm. Understanding the possibility of outcomes, yes.
So, based on the historical data.
Okay, what else? What else can we use? So the answer we got so far was historical data, analyzing outcomes. We claim that it is a degree of belief about the likelihood of an event. Okay? Why do we say that? Why do we say degree of belief? That sounds so almost non-technical. Well, it is quantitative. I would say it is quantitative, but it is our... So uncertainty is our lack of knowledge, and probability, which is obviously very closely related with uncertainty, is degree of belief. Since we lack knowledge, we have some belief that some event might happen, right? And that belief is encoded in the number that you see, right? When we say something is 0.7 probability, that's like saying that that's my degree of belief. Okay? Do you like this definition? Do you not like this definition? Or you have reservations? So there's two schools of thought in this, right? So there's frequentist, which says that relies on data. I think one student mentioned data, that we collect past data and we calculate the number of times an event was observed over total number of events, that experiments. So that is one way of looking at. They're called frequentists, and then the other ones are Bayesianists, who say prior belief informed by data. Okay, so these two events. Probability of failure of a nuclear power plant. How would you find that? It'll be very hard, right? It's a very complex system, and we don't know how different failure modes combine. And so it will be very difficult. But we can actually do risk analysis and use those. Just because it's difficult doesn't mean we won't do it. But what I would suggest is that don't try to use past data in this case. Okay? Or because for a complex system, just because some nuclear power plants failed in certain ways, certain modes, does not mean that future power plants will also fail in those modes. I also do not recommend building a whole bunch of nuclear power plants to collect data. Right? That's a bad idea. So a lot of it has to be our understanding of probability of a degree of belief. And even if you talk about individual components, the operating conditions are not the same. There's many ways you can think about how a degree of belief definition works better. Probability of the Earth being hit by a large meteorite. Again, I would challenge for you to collect data on this. Right? So we are starting to see that our prior data may or may not exist, may or may not apply to our situation, right? So if I showed you a nuclear power plant that is poorly run, let's say, somebody did an audit and they say, you know what, they're not following any safety protocols. Would you use your past data in that case? It's like, no, I'm not going to use past data because these guys are careless. Or you're going to say, I'm not going to use my past data because these guys are much more careful and their probabilities are much lower. Okay? So it has to do with belief. If I give you a coin, what is the probability of getting heads? Huh?
So it depends on how many times the coin is tossed.
No, it does. Time is not important. I'm talking about you get one chance. You're supposed to say, what is the likelihood that it'll... 50%. Why are you saying that?
Because a coin has two sides, heads and tails. Mm-hmm. And when we toss a coin, there are chances that we get either of the sides. Mm-hmm.
We believe that the coin is fair, that's the underlying assumption, right? There's people that can toss coins that will always get heads. Okay? And so, but the thing is that if you don't have any, if you're the term that's used is if they're ignorant about whether the coin is fair or unfair, then 50-50 is a good assumption, right? Because it could be biased in favor of, actually, let's pose it this way. I give you a fair coin. What is the probability of getting heads? I give you a biased coin. What is the probability of getting heads?
100%. Like, it depends on like how biased it is.
I already told you it's biased. And that's all I'm telling you.
So either it could be 0 or it could be 100%.
No, you have to give me one number.
Huh?
You have to give me one number.
So it's not 50%. Because it's correct, it's not 50%. So could you plan like
No further clarification. One case I said fair coin, and you will say heads or tails. Everybody said 50% chance of each. And then in the second, or actually, I say chances of heads. The second case, I'm saying it's a biased coin. What is the chance of getting heads?
so it again depends. If the coin has only heads, like if both the sides, both the faces of coins are heads, then it will be 100%. And if both the
Well, yeah, you're reasoning it properly, but I did not tell you which way it is biased. So it may be biased towards heads,
yeah,
and then you could get
100%.
right, and then you could be biased towards tails, and you have 0% of. So again, your probability comes out to be 50%. There's a 50% chance that it is biased in favor of heads. If you're saying it's 100% biased, it always gives heads, or it always gives tails, your probability of getting heads, since you don't know which way it is biased, is still 50%, right? If you don't know which way it's biased, and I can use the same argument throughout. If there's only two, so this is what this follows from. There's many ways to think about this, right? So Bayesian is basically, I'm saying that's your degree of belief, right? Degree of belief in the coin that I'm giving you and all that. You can even rigorously say, if you look at the maximum entropy probability distribution, you will assign equal probabilities to both events because you don't know. You don't have any reason to believe that it's biased in favor of heads or tails, right? Because I didn't give you that information. So, either way, probability stays a degree of belief, and you can inform it with data. So, if you use the beta prior, I really studied Bayesian probability here. So, you use the beta prior for the probability of getting a head, and then you update it with data. It'll eventually converge. So you might start with, let's say, half probability, and you'll eventually converge at the actual probability. So Bayesianists are not against collecting data. We're just saying that at the end of the day, it is your belief informed by data. It is never purely data because that data was past data, may apply for a different situation. Sometimes you don't have data, okay? So especially for complex systems, it has to be your degree of belief. Another way of thinking about this and understanding this is that imagine a being that knows past, present, and future, right? In some religions, we say that the God of that religion knows the future perfectly, right? So if you ask that entity, what is the probability of rain at 3 o'clock tomorrow? What would they say? If you ask an all-knowing being, what is the probability of rain at 3 o'clock tomorrow, what would they say?
Whatever has will happen tomorrow, they don't say today. They know everything.
Right, so, but the thing is that the question is phrased, what is the probability of rain at 3 tomorrow? Well, the first thing they might ask is, what is probability? Because for a being that knows everything, the concept of probability does not exist, right? Events either happen in the future or they don't happen in the future. So obviously we don't know everything. So it has to be our lack of knowledge, right? That we don't know everything. So we use this definition. And then, so like I said, it is a quantitative definition. It says that you can assign what's called a prior in Bayesian probability, and then you can update it with data. So that model of making decisions is much more richer and correct than any other model, right? So if you don't know, whatever you know, you can encode that in a probability prior distribution, and then you can go from there. So we talked about that already. Okay. So basically, always review probability and statistics, especially people who are doing their PhD or want to pursue higher education. That's going to come handy in a lot of settings. So now we have covered two interesting topics. What is a decision? What is a good decision? No, what is uncertainty? So now we can talk about what a good decision under uncertainty is. Okay. So even the best decision leads to a multitude of possible outcomes, some of which could be bad. Everybody knows that. So what is a good decision under uncertainty?
Minimum impact of the outcome.
Huh?
Minimum impact because of the outcome. Because we do not know what is the outcome. There is an uncertainty about it. At least we can reduce the impact.
Okay, so why wouldn't you focus on the positive and say that maximizes good things? You're saying minimize bad things.
Depends on risk taking it.
Okay. Yeah, okay.
The risk taker is maximizing the positive. Risk
I don't think it's black or white like that. That risk takers and risk averse people. I'm looking for a basic definition. How would you say that the best decision was made, or a good decision was made? What is a good decision under uncertainty? So first and foremost, we have to agree, outcomes tell us nothing about the quality of a decision. Okay, so we are biased as human beings to judge the quality of a decision by the outcomes that happen, right? It happens in sports a lot. Somebody takes a risk and it pays off. You say, oh, that was a great decision. Somebody takes a risk, it doesn't pay off, and you say it's a bad decision, right? So there are many examples of good decisions that resulted in bad outcomes and vice versa. Okay, that does not make it a bad decision. Similarly, there are a lot of bad decisions that end up in good outcomes, and that doesn't make them a good decision. So case one, person goes to a bar and has a few drinks. They decide to call a cab. Would you call it a good decision? They don't want to drive. Huh? So a cab can still get into an accident, right? And then they can still end up in an accident. Case two, person decides to drive. Is that a bad decision?
Yes.
Every day, many people unfortunately drive drunk, and then they're able to reach home safely. So is that a good decision?
They might be reaching home safely, but on board they must have someone else.
Not necessarily. But the whole idea is that, but we have to separate or extricate ourselves from this understanding that outcomes, in both cases, outcomes didn't tell us anything. It was a bad decision when it was made. Besides, you cannot, in real life, wait for the outcome to happen to make a decision. You have to make a decision now. I don't know what's going to happen, right? I say, okay, let's use aluminum here. Not knowing, let's say there's some sort of fatigue failure that I didn't account for, right? I have to make the decision now. I have to analyze it now. Based on what I know now, I make a decision. So whether it leads to failure or not, that's too late to be able to make a decision. Decision was already made. So we judge decisions when they were made based on the knowledge that you have now. Okay? And when a decision is made that maximizes the probability of a good outcome, then you have essentially made a good decision based on your current state of knowledge, right? So outcome bias is ingrained in our head. We feel compelled to judge a decision based on the outcomes it produced. If there's one thing you can get out of this class, or I hope you get multiple things out of this class, but if you, one of the important things you can get out of this class is that separate yourselves or the quality of your decisions from the outcome you received. Okay. Analytically thinking about decisions takes us away from outcome bias, and a decision that is made based on our current state of knowledge using the best preference models that we have is a good decision, and it stays a good decision. Tomorrow you might find something else about a system that you did not know. Maybe there's an effect. Maybe there's a, I don't know, failure mode that you didn't know about. Okay? So not knowing about it and making a decision, and then when you learn about it later on and making a better decision is okay. But of course, that doesn't mean that you stop doing investigations. You should do your best you can, given the time and resources you have, to learn about all the possible kinds of failures that can happen, all the possible things that can go wrong. And if you have time constraints, that's okay. If you have knowledge constraints, that's okay. You can still make a good decision based on your current state of knowledge. Okay, so next thing is decision trees. And I think this is important because this will standardize our understanding of decision making. Okay, so this is what a lot of the textbooks and research articles will use. So a decision tree is a visual representation of a decision problem. Goes without saying. They're standardized, so anyone looking at them can understand what decision is. Okay, so has 4 elements: decisions, uncertainties, arrows, and outcomes. Okay, so decisions we always show with rectangles or a square, like that. Okay, and uncertainty is a circle or oval. Order of execution. So when you're following, okay, what happens next, is shown with an arrow, and then outcomes are with rounded rectangles. Okay. So sometimes people will just leave the outcomes as it is, and they wouldn't draw rounded rectangles. But generally, that's the model that's followed. Okay. So let's do some examples.
So can I just do
Yes. Okay.
Yes.
So let's do some examples. Going out or staying in when there's a possibility of rain. Okay, so this is as trivial as you can get. Just to get familiar with how decision trees are drawn. Another example would be buy a new or a used car. So just elaborating, going out or staying in. Let's say that I'm considering whether to go out or stay in today. Okay. And I'm concerned about whether it's going to rain or not. Let's use our knowledge of decision trees to represent this decision. Okay. So what do I start with? Well, uncertainty, if you knew whether it's going to rain, then it would be an easy decision, right? So you start with a decision, whether to go out or not. You decide before the uncertainty unfolds. So let's say there's 2 possible outcomes or decisions here, rather. Go out or stay in. Okay. Then we say, when we go out, it may rain or it may not rain. When you stay in, it may rain or it may not rain. And you're going out or in does not affect the probability of rain. I hope not. And then if you go out and it rains, your clothes get wet. We're assuming that you didn't take an umbrella. If you go out and no rain, you stay dry. If you stay in, you stay dry regardless of whether it rains or it does not rain. Okay, that's pretty straightforward. So that's just like just getting used to drawing decision trees, and you execute it from left to right. But the arrows tell you what happens at each stage. Okay, or what stage follows what. Okay, pretty straightforward. Now, let's say we change it now. We say that, let's say we make the same decision, but this time I wait to see if it rains or check a reliable weather station. Okay, so I can say, okay, I'm going to sit at home, not go out until I have made sure visually, or check a reliable weather station. So let's say weather stations are 100% reliable before I make a decision. How will the decision tree change? At first, the uncertainty gets resolved, right? The weather station will say rain or no rain. So, and then we make a decision of go out or stay in. And the outcomes in each combination will stay the same. Each combination, you got to keep that in mind. But essentially, when we follow one line, right? So we can say it rained and then we went out and our clothes got wet. We rained and we stayed in and they stayed dry. So you can make the decision anyway, but then you're in a much better situation now, right? That if you waited, you could decide if it's raining and you go out without an umbrella, well, that's on you. And then if it's not raining and you really wanted to go out, then go out because it's not raining. Okay? So just changing the order of execution of the tree occurs because now you waited for the uncertainty to unfold. Okay, so hang on. Better situation is what I have here. Okay, great. So, and I kind of want to make a point here though, that you would think, and then once we start doing probability calculations here, that the weather station may or may not be 100% accurate. Okay, you're probably already thinking that. In fact, for most rain type situations, they're okay now with Doppler radars and things like that. But you could also have a second uncertainty. You said weather station says rain or not, and then you have another uncertainty, weather station is correct or not, and then you have weather station says no rain, weather station correct or not, because they can say it's going to rain and it doesn't rain. They can say it rains, doesn't rain, and it's going to rain, right? So all four possibilities. So the decision tree grows exponentially. You can probably see that. Like, every time you have a bifurcation, it gets really big. And there's software available to do that more easily. But if you're just trying to get comfortable with the concept of what's going on, okay? Thank you so much.